Hello, everyone, and welcome to Lab 2, which is on measurements of space and time. So I'm going to walk through this. This handout is in particular for Physics 207, but it's also applicable to Physics 206. And often the two classes are very similar, so I'll typically just do one video lecture. The only difference is Physics 207, most of your questions will be from the lab manual. And in Physics 206, the questions are written out directly on the lab handout. Okay, but the labs are very similar. Because 206 is a slightly shorter class, there might be some things that 207 does that 206 doesn't do, but you'll have all the information in this video if you're also in Physics 206. Okay, so what we want to do first in this lab is we want to ultimately compute the density of a small aluminum cylinder. So a small aluminum cylinder. And to do that, we need to measure the mass and the volume, right? Because density is mass divided by volume. And to measure the volume of the cylinder, we need to know measurements of the height of the cylinder and then measurements of the diameter of the cylinder. Well, the instrument that we're going to use to measure the height and the diameter is something called a vernier caliper. So let me show you how you actually read a vernier caliper. Now, I'll do this in class as well, but for now, what I'll do, if you're watching this because you missed class, then you're going to have to get this data from your lab partners, or if you can't get the data from your lab partners, just send me an email and I'll give you some data that you can use so you can complete the lab. So if you haven't actually, if you weren't able to sit in and listen to this particular lab live, then you need to get this data. All right, let me discuss how to read the vernier caliper. And to do that, I'll show you the simulation. Okay, so here's the vernier caliper. And obviously the real one's gonna look a little bit different than this, than the simulation, but it's the measurement and how you actually record the length is gonna be exactly the same. So here's the object. So this blue thing is the object. You have two jaws. This one can slide. So this is a slider here. And if you look, there's two scales. You have this main scale, which goes from 0, in this case, through 4, and it keeps going, right? This is in centimeters. And then you also have on the slider here, you have what's called a vernier scale that goes from 0 to 9, right? 0 to 9 in the vernier is called the vernier scale. So what you do is you put the object between the jaws, right? You close the jaws together. And now we want to measure the length of the object. So to do that, what we're looking at is where the 0, this is also called the index. So the 0 on the vernier scale, where does that lie on the main scale? Like, where is that on the main scale? That will give us this length. That's the reading for this length. So if you look at this, see how it's a little bit past the 1.6, like this is 1, 1.1, 1.2, 1.3, 4, here's 1.5, it's 1.6, and it's a little bit past the 1.6. So it's 1.6 something. And by eyeballing it, it looks like it's just a little bit past 1.6. So it might be 1.61 or 1.62 or 1.63. To get that last digit, the hundredths place exactly, what you do is you look at the vernier scale and you ask yourself, which one of these marks, the 0, the 1, the 2, the 3, which one lines up best with any mark from the main scale? See how if you look at this, the 2 lines up best, it matches up best with the main scale. Everything else is off a little bit. So therefore, I would read this as 1.62 centimeters. That would be the length of that object. And actually, that's what the computer got as well. If you can check down here, 1.62 centimeters. Here, let's try another one. Let's say this is the measurement. Okay, so I close the jaw, right? That's my object. I close the jaws. I want to measure the length. So I look where the 0 is. Okay, it's like, this would be like 2.0, 2.1. It's 2.1 something. It looks like it's more than halfway, right? So it might be like 2.16, 2.17, something like that. So you should just sort of like eyeball it to get a rough idea. So to get the exact last digit, again, I look on this vernier scale and I ask myself, which one lines up best? We already know it's probably going to be like 6 or 7. So does a 2, 3, 4, 5? It looks like this one's kind of close. Sometimes you might be off by 1, but it looks like probably the 6 lines up best, right, with any line from above. So then you would read this as 2.16 centimeters. And again, that's what the value is here. Now, if you happen to be right on a mark, let's say, let's see if I can shrink this a little bit. Let's say you're right there. So the 0 happens to be right on this mark. Then you would read this length as 1.7. And then the 0, since it lines up best, you have to include that 0, right? So it'd be 1.70 centimeters. So this instrument has 2 decimal places, right? Its resolution is 0.01 centimeters. So that's how you read the vernier caliper. There's also, I made another little video, again, showing you how to read the vernier caliper and explaining like what that little circular cylinder is that you're measuring the density of. So it might be a good idea to watch the other little video that I made as well. Okay, so either you collected the data and you actually measured the heights and diameters, or you got the data from a lab group or from myself, right? So let's say you have all this data now. So you have the 5 heights, the 5 diameters. So the first question that you're responsible for is question 5. And if you're in Physics 206, the question is written out for you. You're asked to compute the average height, the average diameter, and then the percent experimental accuracy for the height and then for the diameter. So we've done this already a bunch, right? If you forgot how to do this, refer back to the measurement video or the measurement handout, or even lab 1. Remember lab 1, we spent a lot of time practicing how to compute percent experimental accuracy. These will all be to 2 decimal places, right? Because that's the resolution of the instrument. So make sure when you round this, it's to 2 decimal places. And then when you find all the absolute deviations and the average absolute deviation, again, make sure you round to 2 decimal places. And of course, the accuracy is going to be the average absolute deviation divided by the average height times 100, right? That'll be your percent experimental accuracy for the height, and do the same thing for diameter. For your lab report, you're going to include this entire table, right, with all the data. And to help you guys out with this, this lab 2 lab report, which is the first real lab report that you have to submit, I created a sample lab report, right? Of course, you're going to have your own data in it, but it should look very similar to the sample lab report. Like what you submit as a group should look very similar. Okay, the next question that you're asked to answer is question 6, which is the second table here. It asks you to calculate the volume of the cylinder and the percent experimental accuracy for the volume. So actually, let me jump over to the iPad to explain this more carefully. So okay, so it turns out the formula for the volume of a cylinder, I'll call it V for volume, is going to be the area of the base, which is a circle, right? So that's pi r squared times the height. But the problem is we're not measuring the radius, we're measuring the diameter, right, of that aluminum cylinder. So how does diameter relate to radius? Well, the diameter is twice the radius. Or you could say that the radius is half the diameter, right? Diameter divided by 2. So now if I substitute this r in to the equation here, I can write this equation now in terms of the diameter. It's going to be pi times d over 2 squared times h. And if you work this out, if you expand this out, this is the same as pi d squared h all divided by 4. So that's the formula that you want to use to calculate the volume. You're going to plug in your average diameter, your average height, right? Work this out, and that'll give you the volume of the cylinder. Now, the second part of that question, question 6, was compute the percent experimental accuracy for the volume. So how do we find the percent experimental accuracy for the volume? Well, we already have the percent experimental accuracy for the diameter and the percent experimental accuracy for the height, right? And if you notice this equation, the volume is proportional to really diameter squared times height which we could write as diameter times height. So if you remember from the measurement handout or from lab 1, if you want to find the percent experimental accuracy of this dependent variable, in this case, the volume, and it involves either multiplying variables together or dividing variables. In this case, we're just multiplying them. Then the rule is you have to add the respective percent accuracies. So in this case, pi over 4, don't worry about, right? It's a pure number. It doesn't have any error. It's only the diameter and the height you have to worry about. So since volume is really diameter times height, to find the percent experimental accuracy for volume, you have to add the accuracy for diameter plus another accuracy for diameter plus the accuracy for height. So this is going to be the percent experimental accuracy for diameter plus another one plus the accuracy for height. And that will give you the percent experimental accuracy for the volume of that cylinder. Okay, so you're just going to fill in this table. So again, the volume, just plug into this formula. You're just going to plug in your average height and average diameter into this formula. That'll give you the volume. And then to get the percent experimental accuracy, it's going to be your accuracy for diameter plus another one of these, right? You have to add it twice, plus the accuracy for the height. And that'll give you the accuracy for volume. Okay, the next part, now we actually want to compute the density of the cylinder. So now we have the volume, right? We just calculated the volume and we have the accuracy for the volume. So the other piece of information we need is the mass, right? Because density is mass divided by volume. So this is basically question 11. You're going to measure the mass 5 times on electronic scale. And actually this scale will record to 1 decimal place. So its resolution is 0.1 grams. So basically 1 decimal place. So what you need to do is you need to, and this is question 11, you need to average the mass and then also compute the percent experimental accuracy for the mass. Now, what might happen, let's say all 5 values are the same, right? Because you're just massing it on a scale. So it should be fairly consistent, fairly accurate. So let's say all 5 values are the same. That means that your average is going to be obviously that same value. All your absolute deviations will be 0, right? Or actually 0.0 if you're being really careful. So you could write 0.0, 0.0, 0.0, and so on. But then you can't just use 0 here, right? When you average these, remember, you have to always use at least the resolution of the instrument for your average absolute deviation. So if you have a bunch of measurements that have very small variability, or even if they're all the same, then here you're going to have to always use the resolution of the instrument. So in this case, you'd have to use 0.1. So then to find the percent accuracy for mass, it'd be 0.1 divided by this average mass times 100. And that would be your percent accuracy. Okay, then the rest of question 11 is to calculate finally the density, the accuracy for the density, and the percent experimental error. So filling in this table. So again, let me jump on the iPad to explain this more carefully. Okay, so first thing, we need the formula for density, right? And we know that density is equal to mass divided by volume. So this Greek letter rho here, this is what we're using to represent density. So all you have to do to find your experimental density is to plug in your average mass, plug in your average volume, right? And that will give you the density. Think of this as like your experimental density. This is the value that you guys got. The next part of that question wants you to compute the percent experimental accuracy for density. But notice here, we have a formula for density, and it involves dividing mass and volume. And remember, we argued earlier, whenever you have a formula that involves either multiplying a bunch of variables or dividing, it could be either, then if you want to find the percent accuracy for this dependent variable here, you have to add these respective percent accuracies. So in this case, to find the percent accuracy for density, it's going to be your percent experimental accuracy for mass plus the percent experimental accuracy for volume. So you just add those two together, and you have both these values from previous tables. You have this, right, from a previous table, and you have the accuracy for volume from a previous table. So if you add those together, that's going to be your accuracy for density. And then finally, the last part of that table, that last part of question 11, and again, if you're in physics 206, you'll have a separate, the question will be written out separately for you, is to compute the percent experimental error. For the density. And remember, that's when you compare your experimental value that you just got, that's right here, to the gold standard or the accepted value, which we're going to say is 2.70 in this lab. So how do you compute the percent error? Well, you're going to take your experimental value, so whatever this is, subtract 2.70, and then you make it positive by taking absolute value. And then remember, you always, again, you can refer back to the measurement handout if you forgot this, or measurement video if you forgot to do this. You always divide by the accepted or predicted or gold standard value, which is a 2.7, and then times 100. And that will give you the percent experimental error for the density. So now you have all the information for this table, right? You have the density of the cylinder. This is your experimental density. You have the percent experimental accuracy for density and the percent experimental error, where you compare your value, this value, to 2.7. Okay, so, and then that's it for the density of the cylinder part of the lab. In fact, that's all that physics 206 has to do for lab 1. Physics 207, since it's a longer lab, you have one more part that you need to do. We're going to also investigate the relationship between the period and the length of a simple pendulum. So the pendulum is going to be adjusted at 5 different lengths. And actually, if you attend class, you're going to do this using a wooden pendulum, like a physical wooden pendulum. If you weren't able to attend class, we can just do this using a simulation. I'll show you how to use the simulation to get this information. So you can collect your own data. You can either collect your own data or you could use your lab partner's data. That's fine. But the pendulum is going to be adjusted for these lengths, right? So 0 is already in the table here. Everything basically is going to be 0. Then 10 centimeters, 20 centimeters, 30, 40, and 50. And the data that we want to collect is we want the time for 5 oscillations of that pendulum. So we want to fill in this column right here of the table. It's the time for 5 oscillations. Okay, so let me show you how you do that using the simulation. Okay, so here's the website. It's one of these PHET simulations that were created from University of Colorado Boulder. These are really nice simulations. Actually, there's several labs where we're going to be using the simulations. So we want to start the simulation. And there's several options. We're just going to choose the first one, the intro. Now, we don't really need this ruler, so we can uncheck this, like click off the ruler, but we do need the stopwatch. I'm going to put on the stopwatch, and I'm going to move this right above this is like the pause play button, because I want to make sure I can jump back and forth quickly. So I'm going to move it right there. To adjust the length of this pendulum, what you do is use this slider here. So this is in meters, but we know that there's 100 centimeters in 1 meter. So if I want 10 centimeters, it's going to be 0.1 meters, right? If I want 20, it's 0.2 meters. If I want 30, it's 0.3 meters, and so on. So let me just start with one of these lengths. Let's say 30 centimeters, so 0.3 meters. Now, to measure the time for 5 oscillations, here's what I do. I press the pause button first. I press play on the stopwatch, and then I'm going to displace this by a small angle, maybe like 20 degrees would be enough. And now when I hit play here, it's going to start oscillating, and I want to count 5 oscillations. So if it starts here, if it goes to the other side and then back, that's 1 oscillation. Then there and back, that's 2, and so on. I want to count the time for 5 oscillations. So basically, I'm going to start it, and I'm going to stop the stopwatch when it hits 5, right? So I start it, 1, 2, 3, 4, 5. So hit stop. And now I know that when the length is 30 centimeters, the time for 5 oscillations is 5.69 seconds. Okay, and you're going to do this for all the different lengths. Let me just randomly choose another length. Let's say 50 centimeters, so 0.5. So you want to reset the stopwatch, press play so it's ready to get going, move this to 20 degrees, press start, and then kind of quickly move over this so then you can stop it when you need to after 5, right? So start, 1, 2, 3, 4, stop. So when the length is 50 centimeters, the time for 5 oscillations is 7.24 seconds, right? So that'll give you all the data that you need for that particular table. And again, if you were in class, then you just did this using the wooden pendulum and you timed it using, you know, your phone or stopwatch. Okay, so now you have all this data here, right? The time for 5 oscillations, and it's to 2. You want to make sure everything in this table is to 2 decimal places, right? These 3 columns here. So now that you have this time for 5 oscillations, how do we actually find the period? Well, remember the definition of a period is the time for 1 oscillation. So if I take these values and I divide by 5, that'll give me the period. Okay, and then make sure again when you record the values, you round them to 2 decimal places. So these will all be 2 decimal places. And then finally, the last column here is the period squared. So you're going to take these values and square them, right? Multiply them by themselves, and again round to 2 decimal places. All right, so that's all the data. Really, all you're doing is collecting this data, and these are computed, the period and period squared. So now for this part, there's 3 questions you have to answer, 16, 17, and 18. 16 is a plot. Actually, 16 and 17 are plots, they're graphs. So 16, I want you to graph period versus length. So that means period is on the y-axis and length is on the x. Be careful with that. So period is on the y-axis, length is on the x-axis. And if you look in the lab manual, it'll say, do that graph period versus length, and then what is the shape of the graph? And it turns out when you graph period versus length, it's going to be like a parabola. It's like a square root function. So when you do the fit, you have to do a square root fit. Now, we haven't talked about that yet. We haven't learned about that yet. You guys did learn about graphing, right? In lab 1, you did all this graphing. And you have the video on how to graph if you want to look at the video again, if you forgot how to use Pascal Capstone. But let me actually jump on Pascal Capstone right now and show you how to do the square root fit, because that actually isn't one of the options. I want to make sure that you know how to do that. Okay, so most of this you know how to do because we've already done a lot of practice with graphing on Pascal Capstone. But let me show you how to do that square root fit. So again, we're going to go to classic templates, choose this upper left-hand one with the table and the graph here. I want select measurement, create new. We're going to do length. That's going to be on the x-axis. So units are cm for centimeters. And then I want this to be period. And that will be s for seconds. I'm just going to make up some reasonable values here that'll give me a nice square root fit. These won't necessarily correspond to your values or be even close. I'm just making up nice convenient values that I know are going to work out. So let's say those are my lengths. So 0, 1, 4, 9, 16, and 25. And let's say these are my periods. So 0, 1.1, 1.9, 3.2, 4.1, 5.0. Okay, so the usual, right? I want length on the x-axis, so I just select this and I choose length. On the y, select this, choose period. For the title here, remember it's always y versus x, right? So I can call this period versus length. That'll be a great title. If this ever gets, the graph gets displaced, like you're missing the data, remember you can always press this upper left-hand button and kind of centers everything for you. Actually, let me move this out of the way too so that I can see it better. Okay, the other thing is, remember, we don't want these line segment connections. So you hover over a data point, right click, and then uncheck show connecting lines, just like before. We've done this a bunch of times now. And then I want to do my fit, right? Remember, this is the fit icon. To the left of the arrow turns it on and off. Make sure you have it on, but then the arrow allows you to select out the different options. And usually we've been doing like linear and quadratic, but unfortunately square root is not one of the options here. So the way that we're going to do a square root fit is we're going to do a user defined function. So you want to click on user defined, go back to the graph. What it does is it automatically assumes it's linear, right? So you click on the information for the user defined function, it'll bring up this curve editor fit icon here. And you can also get it by clicking on this right here, either or. So let me just click on curve fit editor. And notice that it's giving you a general like linear equation, right? So y equals ax plus b. A is sort of the slope in this case, sort of like mx plus b. We want to change this. We want to change this to a times, so like shift A is a times asterisk. And then we're going to write sqrt for square root, parentheses x, close parentheses. And then hit apply. You can leave the initial guess at 1. That should be fine. And you should see on your graph that it does a nice square root fit, right? So you have this like sideways parabola for the fit now. So it gives you that nice fit. And then remember to put this graph in your lab report, you click on the side, right? Hover over the blue border here, right click, go to copy display, and then you can paste it wherever you want, right? So you paste it into your lab report. Right, so nothing new with the graphing. The only thing that was new that we had to do this user defined fit here where we wanted the square root function, right? So you just write a times square root of x, hit apply, and that should give you the nice fit. Okay, let me go back to the handout. All right, again, so remember question 16 is going to be plot period versus length. That's what we just did. It should be this nice parabola on its side fit, right? Square root function. Question 17 is plot period squared versus length. So this is going to be on the y-axis, period squared, and length again will be on the x-axis. And this one for question 17, remember this one, if I do period squared versus length, that should be linear, right? So period squared versus length should be linear. And then question 18, this is what I discussed in the measurement handout. Question 18 wants you to come up with an equation that gives the period as a function of the length. So a period t in terms of the length L. So let me just remind you of that, how to come up with that. So here, I'll do that on the iPad as well. Okay, so remember that when you do the graph of period squared versus length, it's going to be linear, right? And we know the general form of a linear equation is y is equal to mx plus b. So the y in this case, since we have period squared plotted on the y-axis, that's going to be t squared. Remember, t is our variable to represent period. And then L is going to be length of the pendulum. So that's got to equal m, the slope, right, of that graph. And then the x variable is the length, right? We have length plotted on the x-axis, so that's L. And then the b in this case is the y-intercept, but and you guys should see this, just like with the measurement handout, page 4 of the measurement handout. And when you do your graph, you should also see this. That line, when you do a linear fit, should go right through the origin. So b, we're going to assume is 0. Okay, so that's our equation. T squared equals m times L. Now we want to find, question 18 is give the period as a function of the length, right? An equation that gives the period in terms of the length. Well, I have period squared. I'm close. How do I get period from period squared? I can take the square root of both sides. So I'm going to take the square root of both sides. On the left-hand side, I'm going to get period, which is what I want. On the right-hand side, I'll rewrite this as square root of m times square root of L. Now, you can plug in your m value. Remember what m is. M is the slope of the period squared versus length graph. So period squared versus length graph. You have that value, right? Because when you do the linear fit, it'll give you the slope. You have the M value. Remember, it's pretty much going to be around, it won't be exact for everyone, depends on your data, but it'll be around 0.04. Okay, so you're going to plug that value in for M here, whatever you get, plug it in for M. And then if you expand this out, simplify it out, take the square root of it, you're going to get something, some number, right? Actually, it'll be around 0.2. May not be exact, but around 0.2. And then you still have the square root. Let me do this in black. You still have the square root of L there. So you're going to have T equals some number, something around 0.2 times square root of L. And that's what I'm looking for. That's the equation. That gives the period. So it gives the period T in terms of L, right? And we know it's a square root function, which makes sense because when we graph period versus length, we got this nice square root function, right? The sideways parabola. So that's all that we wanted for question 18 was that equation. And then once you have that, right, once you have that equation, period as a function of length, then you're done for this particular lab report. So you just want to type up this lab report. Only one person per group needs to submit it, okay? Unless you're doing it, let's say you had to miss the lab and you couldn't work with the lab partners, then you could actually submit an individual copy, right? So it's sort of up to you, or you could work again with your lab partners if you want to. And it'll be submitted in class on paper, like a hard copy. If you want help, look at my sample lab report. It should look very similar to that sample lab report. Okay, actually, let me bring up that sample lab report right now just to show you that. Okay, so here's the sample lab report. So very important, make sure your first page is a cover page, right? It has the name of the lab. So this is lab 2, measurements of space and time. And you want to list all your lab partners' names here. So I know who's in the group. So when I record grades, everyone gets the same grade. And then all you're doing is you're answering questions from the lab manual, right? That's in your lab handout, or directly from the lab handout if you're in Physics 206. So the first question was, please describe how you use the vernier caliper to measure the height and the diameter of the cylinder. So just a few sentences, something similar to this. Obviously, you don't want to copy mine exactly, but you want like the general idea, maybe a few sentences, a paragraph describing how you use the vernier caliper to measure the cylinder. Then question 5 was include this data, right? So include a table with all the data. The easiest way to do this is copy my blank table from my Word document, paste it into your document, and then you can fill in with your particular values. And then make sure, this is really important, that you show me the calculations, right? So question 5 was fill in the data table, calculate the average height, average diameter, and the percent experimental accuracy for the height and for the diameter. Make sure you show me those calculations. If you don't want to do everything, like for the calculation part, first of all, most things should be typed, right? In general, you want almost everything to be typed. However, if you really don't like doing equations on the computer, you could leave a blank space and write in these by hand if you want to. Okay, but just equations, everything else should be typed. Question 6 was fill in this data table here and then compute the volume of the cylinder and the percent experimental accuracy, and then show me the 2 calculations. So I show them here. Question 11 was fill in the mass table and then calculate the average mass and the percent experimental accuracy for the mass. Show me the calculation for the percent experimental accuracy. The rest of question 11 was calculate your experimental density, the percent accuracy for density, and the percent experimental error. Fill in the table and show me those 3 calculations. Okay, and actually if you're in physics 206, that's all you had to do. If you're in 207, we also had this pendulum part. So you want to fill in your data table, right? Again, everything should be rounded to 2 decimal places. If you want, you can maybe show me like 1 or 2 sample calculations. So you don't have to show me all these, maybe 1 or 2 sample calculations will be fine. And then question 16 was graph period versus length, and answer the question, right? Which was what was the shape of the graph? You could say like it's curvilinear, right? Or a parabola. And then 17 was plot period squared versus length, and answer the question about the shape of the graph. And then question 18 was to give that formula, give the period as a function of the length. So the period in terms of the length. In this case, I got t period equals 0.203 times square root of L, right? So it came very close to 0.2. And then you want to make sure that you staple or attach your graphs to the lab report, right? So this is, let me zoom in a little bit here. This is the period versus length. Yours should look very similar to this. Make sure you have a title, right? Period versus length, y versus x. This one should be the square root function. And then the period squared versus length should look linear. And when you do linear fit, this is the slope value I use to plug in for question 18, 0.0412. Okay, but they should look very similar to that. So then, staple it together. The beginning of the next lab period, just make a pile up front in the lab, and then I'll grade them and get back to you the following week, right? So just one person per group has to submit a hard copy of the lab report. All right, and that should be it for lab 1. Thanks.